Hi there. So today we're going to be working on pressure loss due to fluid friction in a pipeline. So this is a very entry-level class you're likely to have in your first year of a civil engineering course or even mechanical engineering, probably anything where you study fluid mechanics and in particular flow in pipelines. So we're just going to jump straight into it. And the first thing we're going to do is we're going to consider a cylindrical element with incompressible fluid flowing through it. So we can draw our pipe. So this is just going to be a section of a pipe. It may be continuous in either direction, but really we're not interested in that. So this pipe has an area of A. The direction of flow is from left to right. So we can have flow there. So we're going to call this side 2 and that we're going to call side 1. The length of this pipe will be L, and since we have flow going from left to right, we're going to have an opposing force caused by friction between the pipe wall and the fluid, which we're going to call tau W. And there. And tau W basically is just an abbreviation for shear force, and shear force is the sliding force between two objects, in this case the fluid and the pipe. So the first thing we're going to do is we're going to write down what the pressure would be on both side 1 and side 2. So on side 1 we will call our pressure P, and on side 2, since we're going to have a loss of pressure due to the friction, we'll call our pressure P minus delta P, whereby delta P is representing that loss of pressure. We're going to have two forces acting in this pipe. Now, since we have flow moving in the first place, then we must have what we're going to call a driving force. So the driving force is what is causing the flow to go from left to right in the first place. And this we're going to symbolize as FD. Now, we have the driving force going in one direction, but the system is in equilibrium. So we're going to have an equal and opposite force going in the opposite direction caused by the shear stress, and that we are going to call the retarding force. Abbreviated as FR. Okay, so what can we say about these two forces? The key concept to remember here is that these two forces are equal and opposite. Next, we're going to try and quantify these forces based on pressures and areas. So, the basic formula for force given the pressure in the area is that force is equals to pressure times area. And it's this formula that we're going to exploit and expand in this case in order to calculate the driving force. So let's start with FD, driving force. So the driving force will be equal to the pressure force at point 1 minus the pressure force at point 2. So we can call that F1 minus F2. Now, we know that F1 is going to be the pressure at point 1, which was P, times the area. So we can rewrite that as PA, and then the pressure force at point 2 will be P minus delta P times A. So opening that and simplifying, we'll have PA minus PA plus delta PA. These two will disappear and we'll be left with only delta PA. Now we can write this in terms of the actual pipe geometry. We know that given a circle, the area is going to be equals to pi r squared or pi d squared over 4 if we're dealing with diameter. So we're going to have delta p times pi d squared over 4. So let's just leave that as it is for now, and we're going to find FR and then see how we can establish what delta P would be. So FR is the retarding force that is acting in the opposite direction to the direction of flow. So the retarding force is going to be equals to the shear stress tau times the area over which it acts. But one important thing to note here is that this area will be different to the cross-sectional area we used in calculating FD. Now why is that? So let's imagine we cut this pipe open and we stretch it out totally. So we would have a triangle kind of like that. So this would be the length L. But this width here would be equal to the diameter of the circle, which would be equals to pi d. So we can say that the area is equals to pi dl. Now going back to our FR, so that was tau w, we would have tau w times pi dl. Okay, so that's all very good. But now what we want to really do is to combine these two values so that we can find out what delta P is in terms of pipe geometry and shear force. So we're going to equate those two values, and we have that FD is equals to FR. Therefore, delta P times pi d squared over 4 is equals to tau w times pi dl. So we can cancel a few things there. Pi on both sides, squared there, d there. So rearranging the equation and making delta P the subject of the formula, we would be left with delta P is equals to 4 tau w L all over d. Now this, I'm just going to highlight this formula. What is the implication? What does that mean? Okay, so delta P we can see is dependent on the shear stress and also on the pipe geometry, and the shear stress is going to be dependent on the flow velocity. So tau varies depending on u, the pipe velocity, and the pipe velocity will also affect the Reynolds number. The Reynolds number will determine whether the flow will be laminar or turbulent. Now these are all concepts that will be introduced later on, so do not feel that you really need to worry right now about turbulent and laminar flows. But the most important thing to remember is that our formula shows that the pipe pressure difference is going to depend on tau, and tau is going to depend on u, which shows the implication of flow velocity on pressure difference. So we can say pressure difference relies on flow velocity, which we're calling u. And that's all for today. Thanks for listening, and I hope you learned something good.